Okay, let's take a look at an application of Faraday's law. This one is really popular with AP tests, and it's called the EMF induced in a moving conductor. What we have here in blue are a couple of parallel rails, like railroad type rails, with a bar of some conducting material laid across it, which can slide freely, and a resistance connecting one of the ends. What you might see is this actually creates a conducting loop over here. Now, if we take this conductor and slide it to the right with a constant velocity, we're going to induce a voltage and a current, because essentially this loop over here is getting bigger. The area is increasing, which means the flux is increasing, which is going to give us our induced voltage. And if we take Faraday's law of induction, we can kind of modify it and apply it to what we are doing over here. So I'm going to write this out real quick. The negative sign we're going to ignore for now. We'll talk about the direction in a minute. The N is 1 because this is a single loop. We have our magnetic field going in perpendicular to the plane of our loop, so this thing goes goodbye. And what we're left with is that the EMF is equal to the B field times the change in area over the time. Now the change in area, this thing has a height of L, and the change of area is kind of, in a sense, the change in the width as we slide it to the right times that L. And so I'm going to write this as B times L times the change in area. Now I'm going to do the change in width as a delta W from here to here is the width, and then the change in width over time. Now the change in width over the time, these two together is the speed that I'm moving at. So this whole thing becomes the strength of the B field times the L times the speed. And you can apply this formula to this situation or any situation where a conductor is moving through a magnetic field. Another very typical application is when you have an airplane flying through the Earth's magnetic field, you will actually induce a voltage difference between the tips of the airplane wings, and you can apply this to that as well. Typically, in one of these problems, they might also ask you to find the current, but the current is just the voltage over the resistance, so then you would just take your voltage, BLV, over the resistance. You can also be asked to find the power, which then you could take that current that you just found and multiply it by the voltage again. Before I go any further, I actually want to talk about the direction of the current. The direction of the current in this loop would be counterclockwise. How do I know that? As I move the bar to the right, I'm increasing the area, which increases the flux. And if you recall from the previous video, an increase in flux will be, you'll want to create an opposing magnetic field. So you'd point your thumb away from the plane of the page, and your fingers would curl around to make a counterclockwise current. Now that plays into the next part, because another typical thing that would be asked is how much force do you have to apply to make this happen? So this is your applied force over here. One thing I know, if I'm moving at a constant velocity, that the force has to be opposed by another force, because my net force has to be 0, so I have a force in the opposite direction as well. That force is a magnetic force. This force comes from the fact that once I induce a current in here, I now have a wire with current in it in a magnetic field, which will experience a force. And we learned before that that force is the current times the length times the strength of the B field. The direction of that force would be given by the right-hand rule. If I point my fingers into the page to represent the magnetic field, my thumb would be up, which would be the direction of current through here, which we figured out before because we knew it was counterclockwise, and my palm indeed points to the left, which would be the direction of this magnetic force. So this magnetic force and my applied force must be equal to each other. That's how I get a net force of 0, so that means that my applied force is just ILB, and I figured out I before, and then I would just multiply it by the length and the B field strength again.